we're going to be taking a look at multiplying and dividing radical expressions. Strategies used to expand and simplify products and binomial expressions can be used to extend our knowledge of radical expressions. So just as a warm-up, I'm just going to jump over to polynomial multiplication. Polynomial multiplication is a great tool in understanding radicals. So if I just take my warm-up, x times x, what we notice is the variables x times x, we're just going to simply denote the answer as x squared. Now, 2x times 3x. Now, what happens here is, I guess I'm trying to say, oh, we're going to multiply the coefficients, and then we're going to multiply the variables. Very similar to radicals. So we would say 2 times 3 times x, or more simply, 6x squared. So keep in mind that that's a monomial and that's a monomial. So what if polynomials, we're taking a monomial and we're multiplying it by a binomial? Well, your multiplying pattern would look something like that. In other words, you would take 3x, you'd multiply it by x, and then you would add it to 3x times 1. That's what it might look like. And this would be 3x squared plus 3x. I hope you agree with me here. Now let's take a look at, this is a binomial pattern. You can tell a binomial pattern because each factor has two different terms separated by an addition or subtraction. So it's a binomial. And I would multiply those two, so 2x times 3x. I'm going to multiply the coefficients, 6. X times x is x squared. Now, 3x times 1, well, that's positive 3x. Now, 1 times 2x is positive 2x, and 1 times 1 is 1. So there it is. I sort of expand it, and I asked myself, is there anything that's like? And sure enough, I noticed that these two terms are like. So I would rewrite this as 6x squared plus 5x plus 1. But it's the patterns that are important. And it's also just sort of understanding that we multiply the coefficients in polynomials. Well, the same thing can be said for radicals. But the way that we multiply the radicals might appear a little bit different. So let's get started. I'm just going to take our first example, A. And I know my radicand is 3, and the other one is 7. The index is the same. In each case, we have a coefficient of 1, so it really doesn't come into play. But I can use the product law by writing this as 3 times 7. Or this is the root of 21. Now, can we simplify that? No, because it has the prime factors 3 and 7, and there's no perfect squares that exist that are a factor of 21. So that was very unexciting, but at least we got to see what multiplying radicals entails. So the root of 6 times the root of 10. Now, here, I'm just going to go maybe take a weird way. I'm just going to say this is the root of 6 times 10, and that turns into the root of 60. And then to simplify, I have to take it one step further and say, does there exist a perfect square that's a factor of 60? Sure. And that's 4. 4 times 15. So if you're quick with the multiplication tables, this is a good method. And I could split this up into the square root of 4 times the square root of 15 to simplify, or 2 root 15. Now, unfortunately, this method might not be the preferred method because our radicand goes from 6 to 10 into something larger. And then that larger number is harder, or larger number or expression is sometimes harder to break up. So I'm going to do it another way, and that's through the prime factorization. So I'm going to take the root of 6. And that is 3 times 2. Times the root of 10 is 2 times 5. Now, if you notice, 6 and 10 share a common factor of 2. So that's going to be kind of important. So I could rewrite this as 2 squared times 3 times 5. So I could simplify this into my perfect square. So the square root of 2 squared times the square root of 15. Now the square root of 2 squared is simply 2, and what is left behind is the root of 15. Now, depends which way you want to do it. Sometimes it's good to plan some attack. And A and B differed in a slight way. A, the two radicands did not share a common factor, so we could not create a perfect square out of the factor. However, in B, 6 and 10 share a common factor of 2. So when we factor it and combine the radicands, we create a perfect square. Well, let's continue on. An important question maybe is just going to be asking, do the radicands share a common factor? So I'm just going to multiply this, see, and I see, well, we have the coefficients of -4 and 2, and the radicands are 5 and 11. So I'm just going to take the long way of doing this, and I'm just going to say, well, that's 4 times -2 times the root of 5 times the root of 11. And this just ends up being -8. In other words, multiplying the coefficients and then multiplying the radicands. Now, what's interesting here, I hope that you're able to see that the radicands of 5 and 11 don't share any common factors. 55 does not have a perfect square that is a factor of it. So you can't simplify it. Now, if I take a look over here, and if I just plan a little bit ahead, and I ask myself 14 and 7, I believe those share a common factor of 7. So that's actually going to be really helpful. I'm going to continue my multiplication, highlight my coefficients. So that is really -18. -6 times 3 is -18. Now I'm going to multiply my radicands. And that's 7 times 2, which is 14, times 7. So I can quickly see now that there is a perfect square factor of 7 in my new radicand. So this is really -18 times the square root of 7 squared times the square root of 2. So this is -18 times 7 times root 2. So off the top of my head, I'm going to have to multiply those two radicals. I don't know what that product is, so I have to go 18 times 7. I believe it's 126. So if I don't know the product in my head, I have to carry it out and show my work. So that's -126 root 2. Okay, I think we're sort of on a roll here. So I'm just going to very quickly do E. So if I do E, I'm going to multiply my coefficients. So that would be 8 root 7 times 75. That's the thought that I have in my head. Now, I'm going to ask myself, perhaps, does there exist a perfect square factor of 7 and 75? Well, in fact, if I would have had that thought up here and recognized that 25 is a factor of 75, I could have simplified it. However, I didn't. So instead, I think I'm going to write it as 7. I'm going to break up 75 into its prime factors. And that's 3 times 5 squared. In other words, 3 times 25 is 75. So I'm just going to reorganize this. And move my perfect square factor to the front, so it's easier to multiply and keep my work. The leftover factors, I'm going to multiply through. So 7 times 3 is 21, and there's no way of combining any of the prime factors of 7 and 3 to create a perfect square. So this is 8 times 5 times the root of 21, or in other words, 40 root 21. So far, so good. One more example. And I like this example because we're no longer dealing with square roots. We're looking for cube roots. So we're trying to create a factor that is a perfect cube. I actually like prime factorization here. I'll do both methods, but prime factorization will look like the cube root of 4 times the cube root of 6. So I'm going to combine my radicands, pardon me. Sorry, I made a mistake there. And I'm just going to say this is the cube root of 2 cubed times 3. Or in other words, this is the cube root of 2 cubed times the cube root of 3. Or, since the cube root and cubing are inverse functions, that just leaves us with the coefficient 2. So this would be 2 cube root of 3. Let me perhaps write that a little bit nicer. 2 times the cube root of 3.